I'm Andy Jones. I'm going to take you through the work I did for my master's in Bristol, right here. So I was trying to figure out the cranial anatomy and the function of this pseudosutian Effigia okeeffeae. So for anybody who doesn't know, or realistically has never had the urge to know about the archosaur tree, it essentially has two main branches. The first one has this sort of group of weird like stem birds that comes off it at some point. They then go extinct, and you're left with just the birds at the tip of that branch, which is the Ava metatarsalia. Then you have the second branch, the second main branch, which is the pseudosutia, and you get, again, some pretty interesting forms there. They also go extinct, and you're left with the two terminal branches of archosaurs, which are the birds and the crocodiles. So where Effigia fits in is up in the late Triassic, and it fits in with these sort of really interesting diverse morphologies of pseudosutian archosaurs. So there are a load of them that have similar morphologies to later evolving dinosaurs. So like there are the etosaurs just there that have an incredibly similar morphology to ankylosaurs. And we've got here the ornithosuchians that have a skull that's incredibly similar to, say, large carnivorous theropods. But Effigia is this one, or at least that's what Wikipedia thinks it looks like. And what it looks like according to Nesbitt and Norell, 2006, is this. It's quite gracile, as you see. And if you compare it to an Ornithomimosaur, which is what I've been trying to compare it to, it looks pretty similar. It's, again, gracile. It's got a really large eye. It's got a large orbit. They're both edentulous, meaning they've got no teeth, both got long tail, both bipedal, short arms. So the hypothesis is that was suggested by Nesbitt and Norell is that they are very convergent with each other, and there may be some sort of convergence of ecology too. So what I've been focusing on is the skull of Effigia, because it's involved with feeding, and feeding is generally pretty well constrained and important in ecology, because sort of feeding is very important. You get a sort of evolutionary constraint because natural selection works on sort of very important things to keep you alive, and feeding kind of does keep you alive. So the skull was initially found by Colbert in the 1940s, but it was in the Coelophysis quarry in Ghost Ranch in New Mexico, USA, and he just thought it was another Coelophysis. So he didn't actually take it out of its field jacket. It was only taken out of its field jacket in 2006, when Nesbitt and Norell found that it was actually a pseudosutian species. So as you can see there, that's the skull. It's pretty complete, but unfortunately it's relatively knackered. So what I needed to do to get any kind of functional idea out of this was to reconstruct it. So to do that, well, it was already CT scanned, so I got the CT data, and I hopefully got it to work. Maybe. No. Yes. Oh, well, there we go. So I took all of the individual elements of the skull, segmented them out in a viso, and removed all the sediment and stuff, and then put it all together. And if you've ever used a viso, you'll know the horror of trying to manipulate that many elements together and put them into some kind of semblance of a skull. But eventually I managed to get some kind of skull sorted out, which hopefully should appear on the screen at some point in the near future. But if it doesn't, I'll just keep on talking. So I'll talk you through one of the main features of the skull when it does. No. Try again? No? It was too good to be true anyway. So one of the main features that is preserved is there we go, is this big eye from the original fossil. And you've also got this mandible that has an incredibly large mandibular fenestra. It's still got the edentulous beak. As you can see, it's not quite as crushed over at the back. So when we can compare it to the original hypothetical reconstruction that was proposed by Nesbitt and Norell, we find that it's subtly different in ways, like there's not this bulge at the top of the skull, and also, most significantly, there's the base of the cranium is now curved slightly dorsally. It's also got a much bigger nares than initially thought. When you compare it to an Ornithomimosaur, this is Garuda mimus, which was reconstructed by Andrew Cuff and Emily Rayfield. you find that it's really, really similar, and you've got some of these really similar features, like the quadrate curves back instead of down like this, and in Effigia as well, it curves back once more. You've got, again, the massive orbit in comparison to the rest of the skull and the edentulous beak. So in order to figure out bite forces and things like this, I needed to do a muscle reconstruction. So in order to do this, I used excellent phylogenetic bracketing. So that is a buzzard mandible with associated musculature from a digital dissection. So that's one end of the Archosaurian tree. The other end, we've got a juvenile alligator mandible here with, again, its associated musculature. I also used a more basal myoanatomy using an iguana, well, obviously papers, using the reconstruction of digital dissection of an iguana, jaw, adductor, temporal muscles, and also some hypothetical reconstructions of dinosaur myoanatomy. So bringing all these together, I could get a vague idea of where the muscles attached to, where their muscle attachment points were, where they attached to on the mandible, and then the rest I could infer through sort of constraints in the bone. So I won't go into the muscles in much detail. We've had quite a lot of muscles today. So that's the pterygoideus muscles, both of those. And then we have the adductor mandibulae series. And then, again, we have the pseudotemporalis muscles. And finally, the intramandibularis. If anybody wants me to go into why I put them where I did, then just ask me afterwards. It's fine. So then, to work out the bite force, you have to do what Rob talked about earlier, which is cutting them in half, trying to work out the cross-sectional area, sort of length and all that. And then you end up with bite forces. So the bite forces for the Ornithomimosaurs worked out by Andrew Cuff, Emily Rayfield, and the Effigia bite forces here, they nest quite well with them. It's really, really nice. So you've got the length adjusted bite force just here, which fits pretty nicely. It's lower than Struthiomimus, but higher than both Garudomimus and Ornithomimus. And plugging all this data in to the model, I created a finite element mesh, put all these crazy lines into it, which is all the muscle forces acting in their various directions, acting in the vectors that would attach them to the mandibles. And the output was 3 finite element models for a bite point at the tip of the snout, midpoint, and a posterior bite. And those were all constrained by where a hypothetical Rhamphotheca would sit, based on the presence of nutrient foramina in the original description of the fossil. So here are the results of the finite element analyses. So this one up here is the anterior bite, mid-bite, posterior. And what you can see is a general trend of decreasing maximum stress values. So the high stress values are the really, really high stresses in grey, and then sort of high stresses in red, and then green. Blue is the lowest stress. So what you can see is with a posterior bite point, you get a lot less stress on the skull. And this is kind of strange because with a posterior bite point, you get more mechanical advantage, so slightly more force. And what you notice specifically if we compare the anterior bite point with models of Ornithomimosaurs, again, Cuff and Rayfield, is that the Ornithomimosaurs seem much better equipped for biting at a rostral point. And the reasons for this, I think, are that with this bite point here, you see that the external nares are situated directly above, and you have this posterior part that's incredibly, it seems incredibly strong bone. Whereas with Effigia, you have the bite point here, and then you have this part of bone here, but then you've got some massive nostrils right behind it. And what you see is this thin bridge of the nose. So if you think of it as a cantilever, you've got the bite point coming in here, and it's pushing up, and you get a lot of stress just along here. So the stress is manifesting itself along here. And you kind of have some really terrible stress on the nose. So I am hypothesizing from this that it's not very likely that they fed in the same functional manner. Although they do look very functionally similar, or very morphologically similar, they probably weren't likely to feed in exactly the same way. Which brings me on to my conclusions. So the retrodeformed skull, it differs from the previous description, but realistically that's kind of expected because originally you don't really know what a broken skull looks like until you put it together. Next, the convergence is present, but probably not functionally present. So all of the convergences postcranially are in fact convergences with theropoda in general. So there are no actual convergences specific to just ornithomimosaurs. The convergences in the skull, they are there, but it seems that the skull doesn't really mimic ornithomimosaurs in function. So what this means is that maybe they fed in a fundamentally, maybe they could have exploited the same ecological niches, but they might have, is it this? Okay, I'll carry on. So they might have shared the same ecological niches, but they might have exploited them in fundamentally different ways. So for example, two of the ornithomimosaurs were found to be more adapted to pecking behavior as opposed to biting behavior. So that's not something that I've tested Effigia for yet, but it's something that I would very much like to. Likewise, dietary composition. Was Effigia herbivorous, omnivorous, scavenging? Well, it could be either, I think, herbivorous or omnivorous. But if it is omnivorous, I don't think it would have got anything from scavenging, because the morphology of the beak, it's not a hooked beak. So all the beaked animals that you find today that are carnivorous, they have a hooked beak so they can puncture flesh and tear it and then eat it, I suspect. So with its relatively low bite force, even just biting on some kind of flesh probably wouldn't have been able to, I suspect, this is pretty much just speculation, but it probably wouldn't have been able to slice through it just with quite a flat beak. And also, I want to figure out what the effect of a Rhamphtheca on that might be. It would probably lower the stresses on the rostrum in general. So yeah, that's maybe an interesting thing. That's it. Thank you for listening. Oh, it stopped. Hey. So yeah, I'd like to thank all those people, my primary supervisors, David, Emily, and Andrew, for being really fantastic. Sterling Nesbitt for providing some interesting discussion points. Everybody else around here for providing really interesting pictures and stuff for the reconstruction. And then for keeping me sane, among other things. Thank you.